All right. What'd you do?
Tripped and fell.
Where?
Sidewalk.
You just tripped and fell on the sidewalk?
Yes. He was running in the ring like a little girl. Dude, that's awful.
All right. So last time we were bringing our the two things. Shut up! Bringing the two things together. We've been working with parsing and unparsing expressions, and we were also working with environments, and now we're bringing those two things together where we can now apply a parsed expression inside of an active environment, right? Okay, so a couple things we need to look at here. Let's try to give some meaning to what some of the different players are in our application. I've had several different things open. Why isn't there something in my open recent menu?
You save them.
Huh?
You don't save them, do you?
Sure. Yeah, I always save them.
It doesn't like you. Microsoft Word on the computers is compatible.
All right, so let's look at what are the steps to run a program. Okay? Or for us right now, what are the steps to evaluate an expression? Okay, so what are expressions? Expressions fall into our category, that's our lambda calculus expression, or LCEs. So they fall into several different categories. We either just have an identifier, so that's called a var expression, right? So var expressions evaluate to the value that they hold. That's what a var, that's what it means to evaluate a var expression, right? That is, look it up in the environment. So look it up in the env. A lambda expression, this is where our logic occurs, right? So a lambda expression, this creates a local environment and has a body that may use values from that local environment. Okay? Lastly, we have an Appt expression. An Appt expression is when we more than likely, let's just so we start connecting the dots for us, let's just think about how we are likely to use an Appt expression. An Appt expression is a lambda expression applied to the correct number of parameters as values. So if I have a lambda expression that takes an AB as parameters, and I pass it a 2, 3, I'm extending my environment. The body of that lambda will be evaluated within the variable environment that has bound A to, what did I say, 2, and B to 3. Does that make sense? Okay, so if I have something like this, lambda, well, let's, lambda A, B, and let's just say it boils down to B, like that. And I'm applying that in the, with this, let's just say 2, 3. That is something I would try to evaluate. I would try to evaluate this Appt expression. So it is Appt expressions, well, let's just say these are the guys that actually allow us to fill the environment so that we can execute the body of the lambda in the context of that environment. All right, so if this is our entire world right now, if we're looking at something that looks like this, we have an environment, but the default environment would be the empty environment. That is an environment that has no variables bound, right? All right, so before we can execute, so the body of this guy is just B. I've given us a simple body. And this guy, what kind of animal is this? Cat, dog, lambda expression, app expression, or var expression? It's a var expression, right? And what do we do with var expressions? We evaluate them to the value that they hold, which is found. So that means look it up in the environment. So before we can evaluate this guy to be a 3, we had to add the 2 and 3 to our environment. That make sense? All right. So what does it mean to evaluate this app expression? Okay, evaluating this app expression first notices that we have 2 variables that we are binding in a local environment. All right, and we are binding them to the rands, the operands that are passed in here. So in this case, 2, 3. So we're going to extend our environment. Just let me do pseudocode here, if you will. So we have A2, B3. Here, let's just call that a. Let's just let that fly. All right, that's what our environment has now been extended to. I know we're using this scope-based environment that Amish came up with, which I think is good, but it's really not for human writing. It's made for programmatic implementation. So it's great. We wrote our constructors and stuff for it last time. We'll be able to use it, no harm, no foul. But just let me get away with an environment that looks like this for right now. All right, so we have our environment that we'll have to extend first. So we notice that we have 2 parameters coming into this lambda, and we're applying 2 operators, or 2 operands rather, to this operator, this whole thing. And what it means to apply these 2 operands to this operator means pass these 2 values in for the corresponding parameters of this function. So I'll be extending my environment with an A is 2 and a B is 3. So I'm binding A to the value 2 and B to the value 3. Does that make sense? Once I've extended that environment, then I can actually evaluate the body. And when I evaluate the body, so this means, so we'll call eval, we can call eval expression, passing it the body, in this case, so the body is just B, and the environment that we are evaluating within. We notice that the body in this case is just the var expression. Therefore, since it's just a var expression, we evaluate it in our environment, which is what? Apply E and V. So we pass in B to our environment, and B should send us back the 3. So this guy will ultimately evaluate to just a 3. That makes sense what each production is? So production 1, our var expressions say, look the variable up in the environment and boil down to the value. Production 2, our lambda expression says, extend the environment we're currently in with a new environment, a new more local environment, a scope, a local scope that is bound, that has these variables bound to these values, these guys right here. All right, so that would only happen as a result of what? An app expression, our third production. So the existence of a lambda, which is what we should find as the operator of an app expression, that guy tells us that we have some variables that need binding. The operands of our app expression give us the values associated with those variables that need binding. Does that make sense? So those 2 productions work hand in hand. We don't have, in practice, we don't have a lambda production without first having a app production, app expression production. Okay, because a lambda does not make sense to execute a lambda if we're it doesn't make sense to execute a lamb, unless it's Tuesday or every other Sunday. So it's when you think about writing the program that does something, you can't just have a lambda. We've had these representations we've been working with, but if you actually want to be able to execute the code, we can't execute it unless you've given us inputs. We can write a method, but until you actually call that method with parameters, the method doesn't do anything, right? So if we're trying to do something with it, we're relying on the user to actually give us something that's executable. Okay? So that means that in practice, anytime we're going to be evaluating a lambda, we would be evaluating that lambda in terms of the operands that were passed to it, the parameters passed into it. All right, so we have several steps here that need to happen. So let's kind of do this generically. Eval-expr. We start with an app expression. And an app expression is likely going to be a lambda expression followed by a list of param values. So we'll just keep it simple, even though we've messed around with recursion enough to realize that we might have a lambda expression inside of a lambda expression inside of a lambda expression, blah, blah, blah. But let's just deal with one layer for right now. Okay, so what's an app expression in practice? It's going to be a function that's going to be applied to these values being passed in. Okay, so that's us writing add nums in Java, that's the lambda expression, and then us calling add nums and passing it 1 and 2 as parameters. That's these guys over here. Okay, so evaluating an expression is going to require us to have an app expression if we want to do something meaningful. Okay, now, so what do? We're going to piece this out. We know we have a lambda here. That's the first part, rather. This guy right here. And we know that the lambda has var names that need binding. Let's actually, and we know that the param values are the values that must be bound to the var names. We cannot execute the body of that lambda until we have extended our environment with this new scope. Okay, so the existence of a lambda implies that we will have a brand new scope that's been born. All right? Some functions take no parameters. So that scope's real easy, right? You know, no variables to bind. We'll extend it with a local scope. It still exists, right? Every function in Java does have a local scope. Just sometimes it doesn't come with anything, right? But by definition, a function comes with a scope. All right, those two guys go together. All right, so before we could even think about evaluating the body of the lambda, we need to extend our environment. Okay, so when we're inside the app expression, we need to be able to get the variable names that are going to be in the new environment, which then tells us how many values we expect to have over here. Does that make sense? So if I look at this guy here, and I look at the lambda and say, oh, this guy has 2 variables that need to be bound. That means I know to expect 2 operands here. Does that make sense? Those have to match up. If you pass 3 operands and something is expected 2, Java's happy to yell at you, and for us, let's just, we're not going to do a whole lot of error checking. Our interpreter is going to be happy to just crash. All right. Realistically, actually, if you give too many, you probably wouldn't crash. If you don't give enough, it'll crash. So if we're looking for 2 and you give it 1, The second we start, trying to access the CA, DDDR, or something like that, things are going to go south. All right. So, punchline here is step one is we need to extend our environment before we can evaluate the body. That makes sense? But we're only extending the environment in our Appt Expression production. Specifically when the operator, the first part of it, is a lambda, which I'm telling you practically is the only thing that makes sense. Okay, it's because our language is an evolving language, we're going to be starting with a very unuseful language. For our practices, we may be passing it in expressions that are somewhat useless. Okay, so for us, it wouldn't necessarily be completely from left field for us to have a Appt expression that says AB, like this. But if I try to evaluate AB, which is technically a legal Appt expression, right? Okay, that's a legal Appt expression. This is an Appt expression which contains two lambda calculus expressions. This is a var expression. This is a var expression. If I try to look up A and B in the empty environment, what do I get? Right now we get falses, right? Not found. Completely useless. Completely useless, but technically this guy should evaluate to the list false false. Makes no sense in real life applying our programming language to something. So if we were measuring whether this programming language is a good language, we're going to say not yet. All right, but it's still, we have to start somewhere with our constructs. All right, so effectively we might have something like this. We might say, for a starting point, we might have an Appt expression that starts with a lambda x, let's say something like that, and maybe takes in a 4. Let's say this is the easy one. Okay, so we notice that this guy is of type Appt expression. That's the production type. Therefore, the very first thing, so if Appt expression, which that's what this guy is, what do? We extend the env and then eval the body. Okay? Under what circumstances do we extend the env? Only if the operator is a lambda. Okay? So, if we're dealing with an Appt expression, then if the operator is a lambda exp, then what do? If I hit escape, so that says I don't want to do that, right? And then I press enter, why does it still change it?
You don't know what you want.
All right. I bet you if I press enter here, does the val? I thought it was going to fix it. I'm not even in that part of the... All right, so if the operator of our Appt expression happens to be a lambda, then that tells us we need to extend the environment, then eval the body. If rater is a var expression, just deal with it. If it's a var expression, it's a var exa, all right, then what are we going to do? We're going to apply env. Look up the variable. So here, let's put it in English, since the apply env quiz didn't go all that well. So look up var val. If the rater is an Appt expression, then call eval-expression. on the car and the coder, the second part of it, on the operands and the operators. Okay, so what we're going to end up having in our initial version of our language is something that is only sort of useful. Then we're going to have to start building stuff onto it. So for starters, we're going to have to make our language probably capable of doing math. That's probably going to be our next step, right? So that we actually have legitimate operators to apply to our operands, as opposed to our stupid lambdas that say, well, I'm going to take in a variable x, and what can I do with it? Well, I don't really have operators to do anything with them, so all I can do is resolve them. So if this was my app expression, ultimately this should resolve to 4. That would be the output of that app expression. Extend my environment, giving us a variable x, binding it to 4. Execute the body, which is a var expression. What I do with var expressions, I look up the variable value and resolve to its value, which is 4. Output of program. Completely useless. Make sense? All right, so now we need to write that. All right, so now we've decided that our apply expression, and actually did I write an eval expression yet? Let's call this eval expression to match up with what we just talked about. All right, so eval expression is going to take in a lambda calculus expression and an environment. Okay, now realistically, we're probably going to have something like define run program, and this guy is going to be a lambda that takes in a lambda calculus expression. So, our program is essentially right now a lambda calculus expression, correct? And what we'll do is we'll call eval-exp, passing it our lambda calculus expression and passing it the empty environment. That kind of gets the ball rolling. Hi, I'm a new program. Here's the environment that has nothing in it, but go to town with this. Okay? So that's what run program for us might do right now, where our language is completely encased inside of lambda calculus expressions. All right, so then eval expression is going to take in a lambda calculus expression and the environment in which it should be evaluated. Now that lambda calculus expression should be parsed. It should be a parsed lambda calculus expression. All right, so we need to make sure that when we call our program, so for example right here, we're going to call, just do it this way, run program, passing it parse exp, is that how we named it? Parse exp, and passing it an exp. Oop. Okay, so then we don't need an environment down here because the environment actually gets built inside of our run program. Okay, so this is.
Do you need parentheses around parse exp? Because it's a function.
Oh, yes, thank you. So we're passing our expression to the parse exp function, which will boil down to a parsed expression. We're passing that parsed expression into run program. Run program is going to take that parsed expression, pass it to eval expression, along with an empty environment for it to operate on.
You have to change apply in the eval-exp.
We're about to rewrite almost this whole thing. Yep. Okay. So, understand what we're doing here. This is kind of our handoff. You run your Java program, it goes to main, but before it gets to main, we kind of get a global environment that's created for us. Okay, that's what this run program is doing. It's saying, I'm going to create an empty environment for you, and then I'm going to execute main. So we have our eval expression. Eval expression takes in a parsed lambda calculus expression as well as an environment. Now we need to find out what we're dealing with. Well, if the car of that expression is var expression, if we're looking at that word, because remember it's parsed. So if I'm looking at that production, what does it say to do if we're looking at a var, if we're looking at a var exa, what does it say to do? It says look up the var val. So if it was B, look up the value of B in the environment. Well, what do we have that does that? We have something called apply env up here. Apply env takes in a variable as well as the environment we want it to look up in, and it ultimately boils down to either the value of that variable or a false. Okay? So if I'm currently looking at one of these guys, then what am I going to do? Let's just dump this for right now since we're going to rewrite it. I'm going to boil down to apply env, passing it the variable part of that, which is the catter of my expression, and the environment in which I need to look it up, which is the guy that I'm currently working with in this context. Oh, thank you. Okay. So, if it's a var expression, apply the environment on the catter of that expression along with the environment that we want to look it up in. If the car of this guy is a lambda exp, then what do we do? Well, what do we say if it's a lambda? If it's a lambda, we need to extend the environment and then eval the body. We have a problem here, though. In order to eval the body, I need to extend the environment. What does it take to extend an environment? Step 1 says I need to extend the environment. What are my required inputs to extend an environment?
Scope and environment, I think.
Okay, go less detail. To extend the environment, what am I trying to accomplish? Trying to add a new variable value pair to my environment, right? To add a new variable value pair to my environment, what do I require? I need a variable and a value, right? So if I'm going to add another variable and value to my environment, I need a variable and a value to add. What do I have right now? I have a variable, not a value. Make sense? Row. So if I'm looking at a lambda here, since I don't have all my inputs, maybe I need to assume that my environment that I'm operating in right now has already been extended somehow. We're going to have to do it later. Well, not later is kind of an arbitrary term when it comes to recursion, right? Kind of like Doctor Who, we don't know which time stream we're in, so it's, I'm at a different call of eval expression or whatever I named it here. I'm at the call where I'm actually passing in that lambda expression, expecting to be able to evaluate the body of it in the context of this environment that hopefully has been extended somehow. Make sense? All right, so punchline for us right here, as far as we know, we don't have the tools to extend the environment. We don't have all the data. So all we can do is try to evaluate the body of this lambda in whatever environment's available to us and hope that it's okay. Sound good? Well, punchline is it better because we don't have the tools to extend it. But we still know that we need to extend it. So if we're looking at a lambda here, what do? Well, we call eval expression on the body of our lambda. And what does our lambda look like if we have a parsed lambda? I need the, hold on a second, parse, takes the string version and creates a list. Okay, so the car is lambda exp. The catter, well, the car, yeah, so the catter is going to be our variable list, which we're going to need someplace else, right? But the variable list does us no good right now. Who's going to need that variable list? Whoever is going to be extending the environment, right? That's the guy who actually needs that variable list. For us, it's meaningless to us. We hope that these guys have already been extended in the environment. So what do we really care about here? We care about the car of the CUDR. CADDR. That is this guy right here. The body of our lambda. Okay? So what are we doing here? We're going to call eval-exp on the catter of LCE and the environment that we currently have. That is, evaluate the expression that is the body of this lambda calculus expression in the context of the environment that I currently have available to me. Okay? That's if we're looking at a lambda. If we're not looking at a var expression, we're not looking at a lambda, we must be looking at an Appt expression. Okay? So hopefully we're seeing here that Appt expressions are kind of where all the magic happens, right? All right, so else. We're looking at an Appt expression. We know that the car of an Appt expression must be a lambda calculus expression. By definition, we are not guaranteed that it's a lambda expression production. We know it must be a lambda calculus expression, but we're not guaranteed that it's a production 1, production 2, depending on if you're doing 0 indexed or 1 indexed. We got a funny conversation going on. I see eyes batting back and forth. No, it's Tim and Curcio. Remember, I got an octa-core up here, and that is a euphemism. All right, so now we need to have a cond associated with our Appt expression, specifically dealing with what kind of animal the car is. Okay? If the car is a lambda, we're going to do the magic we've been hoping to be able to do here with the variable value pairs, extending the environment. If it's not a lambda, what do we do with it? Well, let's start with this. If it's not a lambda, what must it be? If the car of an Appt expression is not a lambda expression, it must be what, Abe? Well, I'm fine with that. So it's not a cat, okay? Well, I told you, I started off telling you what it's not. I told you that it's not a lambda expression. So it's not that production. So if the car of an Appt expression must be a lambda calculus expression, it has to be one of those. So back here in our book. Where's our book? Right here. So here's our Appt expression, right? If the car of this guy is not a lambda expression, he must be what? Or an Appt expression. One of the other guys, right? And what do we do with var expressions? Do we call eval expression on var expressions? Yeah. Otherwise, what are we going to be doing here? If we say, well, if it's a var expression, we're just going to do the same crap we did up here. We probably should not rewrite the same code multiple times. We should say, if the car is this guy, then call eval expression on that guy in the current environment. So, cond, actually, let's just do this as an if. So, if the car of LCE is equal to a lambda expression. If it's one of those guys, we're going to do the special stuff. Else, we're going to call eval-exp on the car of LCE and the environment. What about the catter of LCE? If I'm right here, if I'm here, that means that the car was not a lambda expression, so it's one of the other guys. It's either our var expression or our Appt expression. So if the car is not a lambda expression, the catter shouldn't be what? It shouldn't be the parameters for our lambda. If we have a lambda as the car, we should be expecting the catter to be our parameters, right? But if the car is not a lambda, the catter should be some expression, some other expression, right? So really, what do we need to do? We need to call the eval-expression on that guy too. So if I'm not dealing with a self-contained Appt expression whose car is a lambda expression, then I don't have an environment to extend right now. Because I don't have the variables, I don't have the values to extend this guy's variables. Instead, what do? Well, best thing I can do is call eval-expression on the car and call eval-expression on the catter. Hope for the best. Now, the important thing here is that I want you guys to see from this kind of gets back to our structure of how we're doing this. Yes, we're trying to plan ahead on where we're going with this, but at the same time, we have to operate with what can we potentially accomplish with the tools we have in front of us. Because again, we're solving all of our problems in terms of the tools that are available to us. All we can do with the car and the catter, if the car is not a lambda expression, is pass them to eval-expression, especially in our boat where we're assuming that the programmer has passed this legal code. That's all we can do. So that's what we will do. All right, so we'll call eval-expression on the car, and we also need to call eval-expression on the catter. Well, how do I do it? How do I call it for both? Can I just write another line here? Do both of those things happen as part of the else? Or is my evaluation going to basically be a list? If I'm given a list of 2 LCEs, that should probably produce a list of 2 evaluated LCEs. Fair enough? So I'll make a list out of calling eval-expression on the first guy and eval-expression on the second guy, passing both of them the same environment. So eval-expression, go ahead and evaluate the first expression that's in the Appt expression. Here's the environment I want you to evaluate him within. Evaluate the second guy in our Appt expression, and here's the environment I want you to evaluate him within, and just make a list at whatever those come back as. Fair enough? All right. Now we have our special stuff. So if I'm right here, that means I am looking at a lambda expression, which means I do need to extend my environment. Make sense? All right, well, how do we extend our environment? Well, let's go and review our environment extension thing here. So we start off by what? Creating an empty scope, and then extending that scope, and then extending our environment with that scope. Okay, so maybe we want a helper function to help us extend an expression environment. Otherwise, this is going to look extremely scary very quickly. Okay, so let's go ahead and write that. So let's define and extend lambda environment. Well, let's do extend env for lambda. I like that better. That's legit. All right. So extend env for lambda. What's this guy going to take in? Well, he's going to be a lambda expression that's going to take in a couple of parameters. He's going to take in a lambda calculus expression that we know is a lambda, right? And he's going to take in an environment that we're extending. What else do we need? In order to extend an environment, we need the variable names, which is going to be inside of our lambda expression, and we need the values. So where are the values going to be? We need it. Did we have it down here? We're going to be calling this guy down here, right? Okay, so do we have the variables, or the values for those variables here? They're going to be in the cdr of our expression, right? The car of our expression is our lambda expression. The cdr of it will be the list of parameters. That makes sense? All right. So this guy will take in our, I'm lost. So there's our LCE, there's our params, and there's the environment we're extending. Okay. Now, if we want to really be cool kids with this, we won't take in the LCE directly here. Instead, we'll take in a list of vars. Lovars. And this will be lovals, list of vals, along with the environment. Okay? And then this guy is going to do the rest of the magic for extending that environment. And ultimately, this guy is going to produce an extended environment. Sound like a plan? I haven't written it yet, but that's what that guy should do. When we call the function called extend env for lambda, he's going to take in a list of variable names, a list of values, and the environment that we're extending, and he should boil down to an extended environment. Sound like a plan? So, down here, if I'm dealing with a lambda, and I know the cdr is my list of vars, I know the CADDR is the body, right? The car is the word lambda expression. The CADR is the list of variable names. And the CADDR is the body of that lambda expression. All right? So what will I do? I'm going to call eval-expression on the body. The body is the CADDR of LCE, along with our extended environment. Who extends the environment? Extend env for lambda extends the environment. Okay, extend env for lambda extends our environment, and he takes in 3 parameters. The list of variable names, which is going to be our CADR, of LCE. Okay, now I want you all to pay attention here and tell me where I'm screwing up here. Along with the CADR of LCE should be my list of variable names. Then the list of values. Where's the list of values? Should be the cdr of LCE, right? The cdr of LCE is my Appt expression. The car of LCE is my lambda expression. So my cdr of LCE would not be the body yet. I need to get the car of this guy, which gives me the lambda, right? Then I need to take the cooter of that guy, which gives me the, then I need to take the cooter of that guy, and then take the car of that. The CADDAR should give me the body of LCE. All right, so let's look at this on paper. All right, so it's like, I'm not sure, but something in my brain just died. All right, so let's say that we have a list lambda x, and then we take in a 4 here. This is, in our little world right now, that is LCE. Okay? We're looking at LCE where this guy, actually I need to do it this way. If it's an Appt expression, it's going to be Appt followed by a list that's a lambda exp followed by an x followed by a var exp x. I'm pre-parsing our code for us so we can see what it looks like. Carry the 8. All right, so lambda exp x for all right, so that's going to be that piece, and then we're going to have a in this case just a x. Yeah, but I'm trying to think what parse is. Parse expression. If I give parse expression just a number, what is he going to do with that? I don't know, is a number a symbol? I think it's false. Yeah. All right. So in order to do this, well, this is not a big deal. Yeah, this is not a big deal. I'm going to add another production. We're expanding our lambda calculus expression.
So before you do that, Jake noticed something funny, is that we have an expression that we'll never ever get to. Is in that first if statement, because you're already checking that and the one above it.
Equal car LCE.
No, we're not checking this above it.
There you are.
Different cars, different timelines. If I'm here, the car of LCE, I get what you're saying. The car of LCE here would be lambda expression, should just be the car of the car.
Yeah.
No, the car of the cat, the catter. The cooter would be everything but the word app expression. The car of that would be our lambda.
Okay.
Then the car of that would be the word lambda exp. This is the part we're pulling apart right now. What goes into what? All right. So actually, let me, well, here, I'll write it in our code here, then I'll write it in our thing here. This guy is going to actually be something called a lit expression. Okay, I've named it after myself. Okay, this is a literal expression. So literal expressions boil down to themselves. So like the number 4 is a literal. So this would be a lit expression 4, close parenthesis. So this is what our parsed code should look like. All right, this is what it should look like. So that means we're looking at the car of this guy. So car LCE in this case is the word app expr. The car of the, let's see, the cooter of that is that list. The car of that is, so we're going to say the car of the Cooter is that. The car of the cooter is that. The car of that. Yeah. This guy looks like this. LCE is Lambda EXP. The car of the, so we take the cooter of that, that's the list there. We take the car of that, that gets us the Lambda expression. We take the cooter of that, that gets us the, and then we take the car of that, and that gets us the X. So this is the, this is that, right? Here's this list. I take the cooter of that list, giving me this whole thing. I take the car of that cooter, which gives me, no, the cooter of that list gives me the list containing this list. I take the car of that, I just get just my Lambda expression list. I take the, where am I at here?
Cooter of that.
Okay, the cooter of that, which gives me the list whose first element is that list. And then I take the car of that, which gives me just this list. All right, so that's that guy. Is CADADR a thing?
No, I don't think so. Cadre of the cat. CADRA. Just do that.
Could we just do list graphs for this, because they're going to be in the same spot. It's just going to be a list of how many.
So I can say list ref 1 should give me this guy. And then within that guy, I would take list ref 1. It's probably going to be less scary doing that. So really, I want to say list ref. Did we decide it was the list first, then the index, or the index, then the list?
It's and then the index.
List ref 1, 2, 3, 0 should give us a 1. Okay, yep. So it's the list first, and then the index. All right. So list ref of LCE 0 is that guy. List ref of LCE 1 and list ref of that guy 0 gives me the lambda. One gives me that, right? List ref of LCE1 should give me the lambda. List ref of that guy, bucket 1, should give me that guy within the lambda. And then that guy, bucket 1, 2, should give me the body. And then list ref LCE can't use list ref for this part because I have more than one parameter. So this part we're going to have the cooter, right? Appt expression, the cooter of it's going to be just the two guys. The cooter of that's going to be the list containing all my parameters. So this is a CDDR of LCE. And in this particular case, that would give me the list 4. That makes sense? If I took in more than one parameter here, it would be the list. Oh, in this case, it's the list. This is going to get awesome real quick.
We
We have different definitions of
Right.
that word. I don't think you know what it means.
Well, no, hold on. We're going to be fine. We're going to be fine because we're still going to have to call eval expression on our lit expression. Give us our number. So what this actually gives us is not the 4. It's going to give us a list containing the list containing lit-exp 4.
Gotta get it away.
No, this is good.
It
Yeah.
works.
Yeah, but in scheme, I think this is a reasonable way of doing it. I don't think there's anything wrong with this. All right, so this guy here gives us our list of lit expressions. So if I had 2 lit expressions over here, so let's say lit expression 4 and lit expression 5. This guy would give me the list containing lit expression 4 and lit expression 5. All right, so this guy gives me the values. All right. See, this is where it's going to come in fun. Let's just assume that's correct. If I have a list of lit expressions like this, how can I turn that into that? Assuming that a lit expression in eval expression boils down to just the value. So if I called eval expression on this guy, it would boil down to 4. If I called eval expression on this guy, it would boil down to 5. And I can show you that to you real quick. It'll take 10 seconds. So we're just going to add an EQ here. EQ car LCE is a lit-exp. If that's the case, just return the catter of LCE. So we just strip out the lit expression and boil down to just the value that's there. So lit expression 4 will boil down to just 4. Make sense? So back to my question. How do I turn a list that looks like this into a list that looks like this? How do I do it easily? I could definitely use map. How would I use map? Ask somebody else.
Done. One answer for the day. Everybody gets one.
So map it across that with the current environment, right? So I need to get the current environment in there. Actually, do I even need to give it the current environment? Yeah, but since we know these are all lit expressions, I don't actually have to give it the current. Ooh, but they might not necessarily be all lit expressions.
Yeah, then you can just
Down the line, if we think about more complex languages, we might have a mixture of lit expressions as well as var expressions that actually boil down to values. Oh, so exciting. Okay. So we need to map our eval expression across this list, but eval expression requires an environment. So a problem is with map, we can only pass it one parameter, this guy. We can't pass it both. So I actually need to write my own map for this. Because when I map eval expression across this, it's just going to apply eval expression to each of these guys, rather than apply eval expression to this guy and something else. So what I actually can do is I can say map lambda.
Why wouldn't it work with the var expression in there? Because when the var expression.
Well, here, I'll show you where it breaks. So if I say map eval-exp onto, let's just call this this list is this guy, right? Onto that guy. If I say that, eval-exp takes 2 parameters. Takes that and an environment. Right? If we assume these guys were all lit expressions, that would be okay. Okay, that would be okay. But what we really have in this situation is a potentially we could have a var expression in there from another environment where maybe A boils down to 7. Does that make sense? So I really need to evaluate everything in this list given the current environment. So map would be great here if we had a map that could take in 2 parameters. But can I fake it? Can I say map?
Well, wouldn't it?
I think I can do this. Map lambda x, and then eval-exp, passing it x and our environment. Map that lambda onto the cutter.
Or you could just introduce the for each function.
No, we don't do loops.
It'd all be so much happier.
Yeah, this will work. So I'm gonna wrap eval-exp inside of a lambda. So now I'm mapping this function right here onto each element of CDDR LCE. This function takes exactly 1 parameter, which map requires. And what am I going to do with that parameter? I'm going to pass it as the lambda calculus expression to eval expression, and then I'm just going to hard code in E and V, which is a local variable. Yeah, perfect. Huh?
Okay. I don't know if perfect is the word.
No, that's a really elegant solution actually. That's the power of Scheme where functions are first-class procedures. I built a procedure that makes map work for this because my environment is not changing. It's a standard. It's the current environment that this is all happening in. I need to make sure I pass it into a val expression for each of these. But map only works with functions that take 1 parameter. So I've provided it a function that takes 1 parameter, and then I just toss the environment in there for what I do with it. Yeah, we're good. All right. So going back here. So I've added a production here. Now we have something called a lit expression, which means I also need to then go up and add that production to my parse and unparse, which means I need to add that production to my constructors up here. So now I have a constructor for a var expression. I'm going to have a constructor for a lit-exp. And a lit-exp is going to create a, it's going to be a lambda that takes in a lit and boils down to a lit. Perfect. So it's basically the same thing as a var exp from a constructor perspective, but we want to be able to differentiate them in terms of how we call them. And then we need to do parse expressions. So now we have number LCEXP. This guy will create a list lit-exp LCEXP. So now we added that production. So this is kind of showing the benefit of using a cond. Adding a production was pretty easy. All right, and I'll paste all this code on Slack when we're done. I realize we're making a bunch of changes and stuff. All right, so we added lit expression to our parse. We need to add lit expression to our unparse. So eq char lc struct lit expression boiled down to lit-exp catter lc struct. Okay, so we'll use our constructor for that. Now, we're back here down to our val-exp. Val-exp now knows how to evaluate lit-exp. So now we're writing extend env. Yeah. All right, so, let's just, yeah, so let's actually piece this out. So we're going to start off with the lambda guy is this dude right here, right? So if that dude is a lambda, then we're going to eval expression on, we need our body. So where do we, the body is right here. Aye. All right, so eval expression on the body. And let's kick this down a line. Along with extend env, passing it the list of variable names. That's this guy, right? List of variable names. So let's actually kick that down a line. And the list of variable, it takes list of variable names, list of vals. So list of vals is going to be this guy. Oh, beautiful. So that's list of variable names. This will boil down to the list of values. That is mapping this lambda expression, the one that takes in a single parameter, which map requires, onto the CDDR of LCE, which is this guy right here. And we need to turn it into that. And we'll do that by mapping mapping this lambda, which essentially maps eval expression with the current environment onto X. Each of those guys in there. Okay. And then the current environment that we're extending. Yeah, that. So if I'm looking at a lambda, then what I need to do is I want to go ahead and I want to evaluate an expression. What expression? The body of that lambda. In what environment? The environment that is created by extending our environment for lambda, passing it the list of variable names, passing it the evaluated list of variable values, and the environment that we are extending. That make sense? So with that in mind, I should be able to do something like this. Lambda A5. So this is an Appt expression who takes in a lambda and a 5. This should extend the environment A, set it equal to 5. Parse expression should turn this into a lit expression, should turn, whatever. So this should boil down to just 5. Oh, we have to finish writing this guy. All right. All right, so this is our lambda that takes in those parameters. And what does it do with those parameters? Okay, well, we need to create it's up top here, right? We need to create an empty scope, then extend that empty scope with each var-val pair. Well, I thought this was going to be friendly, Amish. What time is this class out? 20 or 25?
25.
All right. Well, we got plenty of time then. Well, actually, what I'm really thinking about, it's not a bad problem. I'm thinking about giving you just that problem for your homework.
So is it supposed to be enough? So in the error expression, do they have bad English?
Of course.
I don't think the parentheses is supposed to be enough.
It's made in Korea, just like everything else.
Scope.
No, scope's good because I want to do this in terms of scope. So what we're going to do is we're going to design our solution, and then I'm going to give you the homework. The homework is just going to be to write just this function. Not all the eval expression, get it working and stuff like that. Just the expression that takes in, or the function that takes in a list of variables, a list of values, and an existing environment, and extends that existing environment with our scope-based environment. So this guy should just produce a new environment. All right, so let's create the solution in English, and then you guys can write it. I'll give you all this code as a starting point, but all you're writing is this one little piece.
On your line there, which says equals car LC lit expression, do you have the parentheses right? It differs from
Where?
right after expression.
Here?
Yeah.
That's right.
All right, so let's plan this out.
Oh, it's like 3.
All right, we should probably pay attention because we got 4 minutes for me to tell you how to do your homework.
Nope, 3.
3 minutes for me to tell you how to do your homework. Okay.
1 minute.
So extending any and v. So we have a list of, we have low-vars, or low-vars. So let's just say low-vars looks like this, AB. As a simple example, okay? And we have low-vals, and let's say low-vals looks like 1, 2. All right, and we want to extend our current environment. So let's say env is currently the empty, well, it would actually just be the empty list. It's our empty environment, right? It's our empty list. So we want to extend that guy. So what we should ultimately have when we're done is this guy. So this guy should produce, through our constructors, this environment. That is the environment containing A1, B2, like that. So that is a list. This is a scope, right? That's a scope. So that's a list containing 2 lists. And how did we do this? Well, we're essentially calling empty scope. Then we're calling extend scope A1. Then we're calling extend, this is extend scope. Then we're calling extend scope B2 on that guy. And then we're taking that guy and we're consing it onto env. So that's what we need to create in that function. How do we go through our list of vars and our list of vals and create them into 2 lists? I think we did an assignment very similar to this way back when we didn't think we were doing language construction stuff. No, except you didn't do it in terms of scope.
Well,
You did.
I did, just didn't just go.
Yeah, so that's fine.
Yeah, wouldn't those be? No,
These are all in the same scope. So this produces, this guy right here, produces a brand new scope with those 2 variable value pairs in it. Yeah, this is right. This is a list of 2 lists.
So that's what extend.
This is one scope. Yeah, this guy here would produce this. These constructors, calling these constructors in this order, would ultimately produce this. That make sense? So for your homework, we're going to write just this piece. Make sense? All right, I'll put this up on Blackboard. I'll paste all the code in there so you have it. And then as soon as that piece is done, we should have a language that evaluates, at least a starting point. And then we need to start adding to it.